Hello everyone, this is Amir from Audio Science Review. I have a review for you today, and that is of this KEF LS50 Meta passive speaker. It retails for about $1,500 a pair, so not cheap for a two-way speaker. So the hope is that it performs great at that price. I must say it's a gorgeous looking small speaker. You can see it sitting over here, and a nicer picture in the frame. This coaxial driver by KEF is a work of art as far as just natural beauty by itself, and then once you put it in this beautifully made composite case, it just looks stunning. I think many people would just buy this as art and put it on shelves instead of actually listen to it. It would have almost as much value. Even the back end of it is pretty in the work that they've done in integrating the port in there. It's offset, it's custom molded, everything. Love the banana or multi-way speaker jacks. They're really nicely done and easy to tighten and untighten. I like the wider distance between them than what some of them use, where you can't get your fingers in between them. The cabinet feels very strong and very dense, which is always good. Our business is to know reliably how a speaker performs, and for that I use this Clipple near-field scanner. This is a robotic machine where you can tell it to basically scan a speaker 360 degrees around, and then computationally you can solve the equations that describe the sound field from a speaker as it radiates. So you can then tell what the sound is like at any distance. And the measurements are made near field, meaning that the microphones are close to the speaker, and the advantage of that is that the sound is much stronger than the noise. So you can make measurements anywhere. You don't need an anechoic chamber. And then when it generates these results, it's actually more accurate than having an anechoic chamber. I usually use about 1,000 measurement points. That takes about 2.5 hours. It's directly proportional to this number. So if you make it 2,000 points, it takes 4.5, 5 hours just for the measurements. And then it takes, at this setting, about 20 minutes computationally for it to do the math and figure out the sound field. If you make it more than that, it takes even longer. The system is self-reporting in that it actually makes some specific measurements in space, and then it computes them from near field and compares the error between the two. With this speaker and many speakers, 1,000 points is good enough. And it was especially good enough because the speaker has a very clean response. The more complex the sound field is, if it has a lot of jagged and deformities in it, the more points you need. And the fact that this doesn't need it means it's a good measuring speaker, as you'll see in a second. So the heart of our measurements is this thing we call the Spinorama. It's a term that comes from Harman and research that they did, and prior to that, National Research Council in Canada, Dr. Floyd Toole and his team. And basically, it's a collection of curves. The most important one of them is this black curve over here that says the on-axis sound. That's the sound that directly comes from the speaker and points at you. And unless speaker manufacturer tells you otherwise and they really know what they're doing, that's the way you should point the speakers. Point them at your face. That's the best sound of the speaker, is what comes at you on axis. And what we like to see ideally is something that looks like that blue line. So we're not seeing that, but what is there for speakers is quite good. Certainly down here, is this little bit of deviation is not consequential. Around crossover, we get a little bit, a few notches here and there, and a little bit of modulation here. And then once the tweeter takes over, it then becomes very smooth and very controlled. And basically, if you get that right, 60% chance the speaker is very good. That's your first order elimination. Speaker that screws up on axis you could just put aside. Chance of it sounding good is very, very low, and it's basically coloring everything. Your ear uses the on-axis, the first sound, as the most important sound to establish tonality of a speaker. So we want that to be right. But we also want the reflections from a speaker to hit all the walls and come back at you, walls and ceiling and floor. We also want that to have similar tonality. It doesn't have to be identical, but it needs to have similar tonality. And when the two are the same, then it's a homogeneous sound. How much of the reflections mixed with direct sound is not as important because they both mix into the similar kind of tonality. And so we call that directivity, and directivity is the next filter for you. You want to look at on-axis, that gets rid of a lot of bad speakers. And then if directivity is good, way up there as far as probability of a good sounding speaker that many people will like. And the LS50 gets there as well. These other curves, like this one, -1, for example, in blue, is the most important, the loudest reflections from ceiling, floor, and immediate walls are summed together with the weighted average, and you get this blue curve. And if you compare this blue curve to the black curve, they look pretty similar. You can actually see that comparison down here. And you can see that line's very smooth. I could almost draw a line through it. It's okay for it to tilt up. That means your off-axis has less highs in it. And that's okay because the tweeter starts to beam and narrow a little bit, and that's fine to get some amount of that because you actually want to see that. So this is very good directivity. We'll come back to more of the spin information, but I'll also do another test, which is I take the microphone and I point it very close to the driver. If there's multiple drivers, there are multiple drivers. I do it for each driver. Here's just coaxial, so I measure both, and then I point one to the back where the port is, and measure them independently so we can see what each one of them more or less is doing. I can't shut off the drivers without turning up part of the speaker, but this gives us an approximation. We see the port in the back, and we see that it nicely augments the on-axis response, the main driver response, which is nice. And the only issue I saw in here was this peaking over here. This looks like the woofer is going down as it should, and then Twitter is taking over, but somehow there's summing above zero, what they should be, neutral. And without being able to separate the two drivers, I can't tell if it's the woofer that's starting to do some crazy things that causes that, or the tweeter. Likely is the woofer. That's a bit of bad news. The good news is that what comes out of the port in the back is very low in amplitude and very well behaved. On many speakers that I measure, especially the ones that are not well engineered, this peak is first of all here where the drivers are much more vulnerable because their levels are coming, and then they actually come up and kiss these graphs. In some cases, you can go higher. Whenever they do that, you basically hear resonances internal to the speaker, which is not something you want to have get out. And here we have many decibels of separation, so some really good absorption inside, and computational modeling has been done by KEF and designed to be able to keep these resonances inside the cabinet very, very controlled and at the right frequencies and so forth. So another good sign that KEF's done the right job. As I mentioned, that blue graph in the spin data, we have a set of reflections that are the most powerful. The other reflections are less powerful, meaning, let's say, it hits the right wall, then it hits the back wall, then it comes at you. By the time it gets to you, the levels are very low. So we care mostly about what these immediate surfaces are, and I've drawn a line through what you want, and the green curve is our total sum of all those reflections, and we see that it more or less matches that. It has the same little bit of wiggliness in the middle that a perfect speaker wouldn't have, but otherwise the two are similar, and that's why we get in this good directivity. We'll come back to directivity a little later. There's been research done by Harman in correlating and computing what a predicted in-room response would look like based on the first two measurements. All the measurements I've shown you are anechoic, meaning that they assume no reflections at all, but we're interested in sound of a speaker in a real room. So statistical models been developed what rooms more or less look like, and that's where these reflections come from. If we take these and sum them with special formula with the on-axis, we get a single graph that says, look, likely if you put this speaker in a typical room, you're going to get this kind of response. We always want it tilting down, and we're getting that, and we want least amount of variations from this line. So again, this little mid-region has a little bit of imperfections in there, and I'll try to quantify these when I get to my listening test section. But otherwise, this is the kind of curve we want to see. As a note, studio monitors are designed for professional applications, tend to have a flatter line. They believe in doing nothing that's different both on and off axis, and that's fine too. I find them enjoyable just as well, but from typical hi-fi listening, you tend to want to have this sloping down to have a little bit less highs than you would otherwise on this thing. So we now get more of drill down into directivity, and here basically we're plotting every 6 dB drop in amplitude in a horizontal axis. So if I look at the speaker and I go left and I go right, and just show you 6 dB drop-offs, what does that look like? And what we want to see is a stack of these curves that look similar. But more importantly, the red one, which is the minus 6 dB one, we want to see that as sort of as flat as we can get it. That means the directivity is uniform and is controlled. The speaker isn't getting wider, then narrower, then wider. When it does that, the frequency response is changing off axis, and you don't want that. So this KEF LS50 Meta has very good control of that. There's a little bit of cost to that in that when you control that, oftentimes the angle gets small, and it is a bit small horizontally at plus or minus 50 degrees. So you want to, again, point these speakers at you. You have basically plus 50 degrees, minus 50 degrees. That's good. Any more than that, then you're going to lose a fair amount of your energy in the higher frequencies. So not a bad trade-off at all, but just be mindful of that. Same graph can be plotted with a lot more resolution and then color-coded. This graph is the same as this one, and we can see it visually, maybe easier that, you know, where the sound energy is going. It's just basically just funneling towards you at a very controlled manner. Now, typically two-way speakers with a tweeter and woofer, horizontally they can get you pretty graphs like this, but vertically they tend to be atrocious in that as you move up and down, the distance from the measurement microphone to your ear changes if the tweeter's up here and woofer's in here, and how the two mix will change. So you wind up having a very erratic and torn up vertical directivity. Coaxial drivers don't have that problem because the tweeter is in the middle of the woofer, so whether you deviate horizontally or deviate vertically, you get the same measurement, and so they do superbly in here. But at the same time, know that the science for horizontal dispersion or directivity being good is very strong. Vertically, we tend to not be that picky about it. In my room, I also have a thick rug on the floor anyway, so the floor bounce is not there, and I have high ceilings. So it's not as material for me. But hey, it's a bit of goodness. You take it. It comes for free in a coaxial driver. A new measurement I've been showing, as I mentioned, the clippable and near-field scanner computes a full 3D sound field for the speaker. So I can ask it to give me what the entire sound field looks at any frequency. And I've chosen to show that to you at 1,000 hertz, 2,000 hertz, and 3,000 hertz, sort of the critical mid to upper frequencies. And you know, an ideal speaker would either look like a globe or an oval. We don't get that. We get, you know, wiggliness in here. Since I've started doing this, the first few speakers I did them on, they were really, really deformed. So what you want to see here, as smooth and as globe-looking or oval-looking shape as you can get. You can see how good this one more or less is, a little bit out of whack in here. Here you can actually see it much better at 3,000 hertz. Just a nice shaft of energy pointing out here, nothing from up, nothing from top, and not much else at the back. If we had strong diffractions, corners were sharp and radiating, or, you know, strange things happening, you would have, you know, deformations up here, you would have red up here, and so forth. So this is very, very well behaved on this thing. Distortion. KEF advertises that the Meta version of LS50 actually has lower distortion. Unfortunately, when I measured my original LS50, I didn't make the measurements as good as I'm making them, so I can't compare the two. What's there is quite good, below 200 hertz. Above 200 hertz is very good. I have this threshold I draw at 50 decibels, and you can see above 200 hertz distortion is very low, and it just drops off the chart down here at 86 dB SPL. At 96, it's clearly getting unhappy, and so this is not a loud playing speaker, and I'll get to that when I talk about listening tests. These graphs, you can interpret them, get a rough idea, but getting a precise idea, the ear works a lot better when it comes to this kind of distortion. Impedance is low. Two-way speakers, or modern speakers in general, they're all around 4 ohms or so. This one drops to 3.7 ohm, and it stays 3.7 ohm for this whole broad region between roughly 120 hertz and 600 hertz. So a lot of the bass energy, where a lot of volumes in the music, lands in this area, and is going to strain your amplifier. The other thing is going to strain it is that if we go back to in here, is the sensitivity of the speaker. This is around 83 dB sensitivity. Usually I like to see 86 dB as an average, low sensitivity speaker. So this is not an efficient speaker. You tend to get more accuracy if you can bring levels down in the speaker, and compromises are made to get accuracy, but you lose some volume playback capabilities. So know that you need good, powerful amplifier with a lot of wattage. Don't think it's a small speaker. You can drive it with a 30-watt amplifier. It'll produce good volume for a bit. As soon as you turn it up, you're out of juice. I'll use a 1,000-watt amplifier just to give you an idea. So that way I know my amplifier is never the limitation. It's, if something sounds distorted, based on volume, then it's because of the speaker. Yeah, I'm not a fan of time domain displays, but people want to see them, so I've shown them in here. So, but just quickly looking at it, wherever you see these lines extending, it means you have resonances. But if you also look up here in the frequency response, whenever there's a resonance in here, usually is a peak over here anyway, and you could have guessed that there were going to be resonances there. But, people like to look at the pretty 3D graphs, and there it is. Now, let me get to the listening test. I have a set of tracks that I use for evaluating both headphones and speakers. I always use the same tracks. I always start with the same tracks. And the first 10 tracks are so religious. Basically, I listen to them. I know what spots in them cause what. And I must have listened to them thousands of times. There used to be music I like, now it's music I hate because I listen to it so much. But anyway, it's important to listen to the same track all the time, so ears at least have a chance of getting calibrated to what they should sound like. And usually on the first track it's a female vocal that I like to use. And if the speaker is good, when I listen to the first track, I'm 90% there in assessing, the sound of the speaker. But we got to verify. So on this speaker, it just sounded wonderful. I'm sitting there, I'm done basically. I could just listen to it and enjoy it. But we want to verify that. The measurements said it would be a great speaker. I might listen to us or agreeing with it, but we still want to verify that, what the effect of these things are. Are these frequency response errors a problem or not a problem? So I created an EQ just to fill this hole, take this bottom and bring it up here so it's flat. And to do that, it's such a narrow filter, I had to use a parametric EQ with a Q of, I think 8 or something like that, 7 or 8. At first I created it with a Q of 4 or 5, and that means that it raised the levels from here all the way to here, and that had an effect. But by the time I tuned it so that it was just this whole, there was a subtle effect, and if you recorded them and had me do an A/B test, ABX test, I'm sure I could tell the difference. But, as far as general tonality of the speaker, it just simply was not consequential. It wasn't even worth the effort for me to capture it and put it in the review. So, it doesn't need equalization from that point of view. And this basically, the reason for that is that our auditory filters that we use in our hearing, their bandwidth starts to get wider in that. So essentially they're averaging big chunks of the spectrum. They're not like a spectrum analyzer like this measurement is. And it can't, it basically can't distinguish much. Again, probably a little bit of tuning you could do. I wrote in the review, if you've got time and these are speakers you're going to live with, you could develop a little bit of EQ and, pull this whole region up, and maybe all of them combined, 4 or 5 filters would make a subtle improvement. So the measurements are speaking the truth, a little bit in here, but in grand scheme of things, it's a speaker, you sit back and listen to it. So I listened to it and it sounded quite good. And I was ready to just give the star rating to this till I turned up the volume. At first, it handled it very well. The kind of music I was listening to was sort of jazz and that sort of instrumentation and vocals. It handled them very well. I only test with one speaker because our hearing is much more, has much better acuity when it comes to detecting tonal characteristics of the speaker when you listen to one speaker. And so I'm listening to the one speaker, and it's able to fill a large room with very good volume. And so I was very pleased with it. One thing you can tell is that little woofer, because it's reflective, you can see it from pretty far when it's vibrating, and when it moves, it actually separates from the tweeter that's in the middle, because they're 2 separate drivers. And it's sort of a little disconcerting when you see that gap in there. But anyway, you have a good visual indication from many feet away how much this thing is working, unlike a black, woofer. This one, you can see it move. And when it moves just a hair, things are okay. The moment I played anything with deep bass and I could see it move a little bit more, where it went beyond vibration to actual movement, I could tell the tonality of bass changed. Turn it up a little bit more, the tonality changes even more. And one click past that, and it crackles. Scary crackle. I let it crackle for just a second, and it's one of those things where, you think your world's come to an end. Luckily, the speakers are very robust, and the crackle comes from the fact that it just comes out, the winding comes out of the magnet just enough, and it just snaps back. And so there is a price to be paid for a coaxial driver this small. It can only move that much air. It plays cleanly, so you tend to want to turn it up, and you get it to that clipping point where it just goes crazy. It gives you some warning in that the bass tonality changes. The deep tones that I was hearing, they start to get lighter in characteristics because harmonic distortions of the bass at higher frequencies, so the tonality of the bass becomes higher pitch in nature instead of boom, 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 bub, bub, bub. It's sort of, I don't know, I can't make the sounds. But anyway, it's a good thing. By the way, if you want to learn to be a good listener, find the worst case situation and turn it down. You can hear that effect a lot better than going up. So with this distortion, if you turn it up before it crackles, and then listen to the bass, and then you lower the volume, that change is much more pronounced, and you can just easily, first you can hear the artifacts at that loud volume with no placebo, no doubt. You're hearing it, you're at the limit, you're at the limit because it's just not happy. And then you gradually lower the volume, and you can see how it exponentially drops off, and then all of a sudden the sound is fine, and then further reduction in volume doesn't improve fidelity. So you're at the limit, and what that limit sounds like, and you bring it down. So I would be happy with these for everyday use as is. There's enough bass there, enough volume, and if you put 2 of them in a room, I only had one, it gets even louder. But if it's the only speakers you have, and this is all you have it for, then a subwoofer is definitely advised. That's a can of worms in how you integrate it with something like this. If you have an AVR with automatic EQ, that's one way to do it. Otherwise, manual process will require work in setting up the crossovers and everything. But it needs some relief. But again, for everyday use, it's a secondary room, or it's your primary system, but you don't turn it up very loud, I think it's full range enough to enjoy a lot of music and not feel like, you know, you need to get a subwoofer. There are two-way speakers I test that just fall apart so fast, or they lack so much bass that, you know, you have to have a subwoofer, and I don't like those speakers at all. So where does this net out? At low to medium to even medium loud volumes is exceptionally good speaker. You'd have a hard time getting a better speaker. It lands way on top. It's just that when you turn it up, it's gonna fall apart, and so it depends on your expectations. If you're never gonna turn it up that much, you never want the floor to rattle and move under you, and you feel the music physically, then these are extremely good speakers, gorgeously built, you know, from a great company, and, you know, get it. I was not a fan of original LS50. Its measurements are far worse than this, and I never liked the sound either. Even though so many people loved it, I think they were just looked at the look of it and liked that more than sound, or they're not skilled in listening to speakers. I don't know, but it's just so nice to see that, you know, KEF recognizes it and you know, came up with this. I think I have the original LS50s here. Do I have a link to it? No, give me 1 second. No, I guess I can't find it quickly. Anyway, the original LS50 review is also here, and you can go look that up. You'll see that the frequency response went up and down. I mean, it was just nothing like what I expected KEF to be producing. I was very surprised how poor that frequency response was. It wasn't just too much highs or too much lows or anything. It just literally was wavy going up and down. So it's very nice to see them improve it. $1,500 is a lot of money though. So, you know, you do have to make a decision whether you like that or not. Okay, so hopefully you found this review useful. I enjoyed my time with it. I'll be sad to be sending it back. And see you in a future review and video. Bye-bye.